Welcome to the remediation packet for Unit 9. It says, what are the divisions of the electromagnetic spectrum? Remember, the electromagnetic spectrum contains all parts of what we consider to be the electromagnetic radiation, including radio, microwave, infrared, visible, UV, X, and gamma rays. Now, if you do the red Martians invade Venus using X-ray guns, it makes it very easy for you to remember, and it actually puts in order for you from increasing lower frequencies to higher frequencies as asked in part B. Now it says, what is the part of the electromagnetic spectrum that has the greatest ability to penetrate a solid object? You should be able to say that's gamma rays, and you should be able to tell me why. Next it says, what is the speed of all electromagnetic waves? And that is the constant 3 times 10 to the 8th. And we're going to assume that we're in a vacuum at this point. So 3 times 10 to the 8th meters per second is what it is for all electromagnetic waves. Radio waves, microwaves, all of them travel at the same speed. Next, it says calculate the time it takes for light to travel a distance of 1.8 times 10 to the ninth. You should realize that since I have a constant speed of light, I can use the constant speed formula from at the very beginning of this year, where you have speed is equal to distance over time. You have the speed of light being your speed, and then you have your distance right here, and you can actually solve for the time. When you solve for the time, you should solve for about 6 seconds. Next, it says calculate the distance a light wave can travel in 5 minutes. Now you should realize that 5 minutes is not a standard unit for us to work with, so you're going to have to convert minutes into seconds because seconds is our standard unit of time. You can still use the same equation, speed equals distance over time, where the speed of light is still the same speed. And if you do it correctly, you should get something along the lines of 9 times 10 to the 10th meters. It says, what is the relationship between wavelength, frequency, and velocity? Wavelength, frequency, and velocity is c equals lambda f, where c is equal to the speed of light, lambda is equal to the wavelength, and f is equal to the frequency. So now it says, what is the frequency of a light wave at 610 nanometers? So you should realize that 610 nanometers is not a standard unit. Instead, you have to convert from nanometers, where there's a billion nanometers, into meters. Okay. Once you've converted, you can plug in our value for the speed of light, which we've talked about earlier, and you can solve for the frequency. If you solve for the frequency correctly, and it's very important that you spend some time working with the exponents to make sure you do it correct, you should get a frequency of about 4.9 times 10 to the 14th hertz, which is our unit of frequency. Next it says, what is the wavelength of a 5.8 times 10 to the 15th hertz photon? So we're going to use the same equation, and if you do it correctly, you should get something along the lines of 5.2 times 10 to the minus 8th meters. Okay, next, if we look at the wave properties, it asks us to draw the Doppler effect. The Doppler effect, normally waves are emitted in 3 dimensions in an equal spherical pattern. Okay, but whenever the source is moving, in other words, this dot is moving this way, the waves become compressed in front of it and extended behind it. So you have the waves closer together in front of the object and extended further out behind it. So an example of where this becomes useful is particularly radar. Whenever they talk about using Doppler radar, what they're using is this idea of the waves closer together or farther apart to tell how fast a storm system is moving. Next, it says it wants us to do it for light wave interference. So if you have a light wave right here, and you have a light wave, change colors just to make it a little easier. If you have a light wave right here, those waves will interfere constructively, which means that the resultant wave, which you get as a result, is going to be larger than the individual waves. And how this is particularly useful is the generation of color. Okay, whenever you have red plus blue, that makes magenta, which is kind of a purplish color. Next, it says refraction. Refraction should look like something like this, where the light wave bends, and it's useful in glasses. For mirrors, you have the law of reflection. The law of reflection states that theta I is equal to theta R. In other words, the angle that a light ray hits a mirror at is the same as the angle that it reflects at. So, as a drawing of this, for a flat mirror, you can see that the angle that it comes in at and the angle that it leaves at have to be the same. In other words, theta I is equal to theta r. Now, whenever you measure with reference to this thing right here, which is called the normal line, where you draw a line that's perpendicular to the surface of the mirror, and when you measure from that, this will hold true for both curved mirrors and flat mirrors. As a result, you get rules. And the rules for those ray diagrams, you draw a line parallel to the principal axis, it reflects through the focal point. Any light ray through the focal point will reflect parallel to the principal axis, and it's because of the law of reflection. Now, if you notice, these two light rays that I've drawn don't actually intersect. They intersect behind the mirror, and when they intersect behind the mirror, it creates something called a virtual image. In other words, the pretend intersection of those light rays behind the mirror when the light can't actually go behind the mirror. Next, it says, what is the index of refraction? And the index of refraction in this case is a ratio of the speed of light in a vacuum and the speed of light in that particular material. So you're saying how much faster is the speed of light in a vacuum than to a given material. It says how can you bend how can you bend a light ray towards the normal, and how you would do that is you would put it in a more dense material. So if this has an index of refraction of say 2 and this has an index of refraction of 1, it will bend towards this normal line. Do you see how the angle actually gets smaller as you bend it towards the normal line? Finally, a ray diagram for lenses. Parallel goes through the focal point, straight through the center. There's your intersection. And once you have your intersection, you can see that this is an upside down image. Okay, now since the light rays actually do intersect, we call that a real image. And if you look, it's upside down as well. So you should proceed on to the independent practice. And if you have any questions, make sure that you see your teacher.